Welcome everyone. I'm Zihong, the Business Development Manager at East 101, and I will be the moderator for the webinar today. Good afternoon, good morning, and good evening to you, depending on your time zone. If you haven't done so, please make sure that you pin the presenter, Mr. Rafil Elyas, the one with the picture, as the main screen, and also enable the fit to frame view so that you get the best view, the ratio of the content that we are about to show. Instructions will be available in the chat. Should you need any help, please type !mark and help to bring it up. And to open the chat box, please look for the icon that looks like a speech bubble in the bar with the microphone and video controls. So once again, thank you for attending our event. I'd like to welcome everyone to our first webinar under the East 101 webinar series. The COVID-19 pandemic has impacted the industry in many ways, and while this has posed some challenges, it has opened up more time and opportunities for continuous learning. So we are glad to see you here. If you like our content, we hope you will help us by spreading the word. For those of you who might be new, we are East 101, and we are a specialty consulting company focused on providing advanced process engineering and flow assurance consultancy services. We work primarily in the oil and gas industry, and we deliver process simulation technology solutions. We were founded in 2003 by engineer Rafil Elyas, and we have offices in Kuala Lumpur, Barcelona, London, Brisbane, and Houston. Our track record includes projects which cover transient simulation-based engineering services, dynamic simulation, flow assurance analyses, operational assistance, especially OTS, or operator training simulator solutions, which are an important factor behind safe and cost-efficient operation, as well as process simulation training. You may recognize some of our satisfied clients here. If you have any inquiries, you may contact either myself, Lee Zihong, or my colleague Avinash at the numbers and email address shown on the screen. More information will be available on our website, www.east101.com. Through our webinar series, we hope to cover a wide range of topics from upstream process design to downstream and refining, monitoring and surveillance, as well as analytics and AI. Our webinars are scheduled to take place every Wednesday from 4 to 5 p.m. Malaysian time. Our next talk has already been lined up. The topic is analytics and machine learning in the oil and gas industry. The speaker will be Dr. Anwar Hamid, our very own process engineering manager, who has been invited to universities to speak on this topic as well. Kindly mark your calendars for the 3rd of June, which will be 2 weeks from now, as our Muslim friends will be celebrating Hari Raya next week. And the time will be 4 to 5 p.m. Malaysian time. So before we get into the webinar, here are a couple of house rules. We have one speaker this evening who will be speaking for about an hour, followed by a Q&A session. We kindly request that everyone to stay muted to avoid any noise and interferences. If you have any questions throughout the presentation, please put them in the chat box and it will be addressed by the presenter at the end of the webinar. If at any time anyone experiences difficulties, please check your internet connection and reconnect to the webinar using the same link. If you miss anything, don't worry, the recordings will be available on our website under the Events tab. So today's speaker is Engineer Rafil Elyas, the founding owner and principal engineer of East 101 Sendirian Berhad. Since graduating from Syracuse University with a bachelor's degree in chemical engineering, Engineer Rafil has accumulated 30 years of experience in the industry, as well as 15 years of formal training experience when he lectured for the John M. Campbell Group, and currently runs training courses via East 101 University. He is currently an industrial advisor and adjunct lecturer for several universities in Malaysia, as well as a chartered engineer and a fellow of the Institution of Chemical Engineers, IChemE. Without further ado, please welcome Engineer Rafil Elyas.
Thank you very much, Zihong, for that kind introduction. Good afternoon, good evening, good morning. I'm not sure where people are dialing in from. I'm seeing a lot of people from this region. I'm seeing some old friends and people that I know from here, from Singapore, from Indonesia. At least I've been noticing on these pop-up things. So I'd like to thank you for coming. And this is the first time I'm actually doing anything like this. So apologies if anything goes wrong. If there are any issues with regards to the connection or any IT related issues, just punch it in the chat box. I've got some people monitoring this. Yeah. So this is the first in a series of webinars that we're going to be conducting over the next few weeks. I guess next week we won't be having anything because it's going to be Raya. So we'll be continuing like on the 5th, as Zihong had mentioned. Yeah. Okay. So today I'm going to be talking about process simulation because that's something that I've been doing for a while, and that's one of the few things that I know how to do reasonably well. I've got a fairly narrow set of a very narrow skill set, and that happens to be within process simulation and process engineering. So I'll be talking pretty much about how we should prepare ourselves before using a process simulation tool or process simulation software to design, troubleshoot, or optimize our processes. So I've organized this talk into the following areas, the following topics. The first is something I'm going to call science fiction and fantasy. I figured all engineers like that. I'll also be briefly going into some of the typical uses of process simulation. I'll be talking about some of the corresponding software tools that are used for those particular simulation activities. And this will be covered in process simulation usage. Now, after that, I'm going to run through a couple of examples that demonstrate the fact that simulation tools are just tools. Simulation software can't anticipate our concerns. They can't read our minds. They can't understand what we want, and they will definitely not be able to correct for a poor problem definition or lack of engineering understanding. Software simulation software are just tools, just like a screwdriver and a wrench is a tool. Saws are just tools which are used by carpenters and craftsmen to create things. So these simulation software applications are just tools, one of the many tools in our kit as engineers that we use for our day-to-day activities. And one of the things I'd like to point out in this section is essentially, I'd like to stress a point that these tools are not oracles. Yeah, process simulation software are not oracles. They can't tell us everything about what's going to happen. So after I after I talk about these particular concerns, I'll go into what I'm calling the 10 commandments of process simulation. Okay. So the first thing, as I mentioned, is this topic, which I like to call science fiction and fantasy. Science fiction, the science fiction genre, movies, books, comics, or graphic novels, typically portray computers as intelligent, sentient beings, like HAL 9000, if you're old enough to remember 2001: Space Odyssey, or most recently, for those of you who are more inclined towards the Avengers, Ultron, an intelligent machine intelligence. Now, if you're 50 or above, you might recognize the guy in this slide. This is Chief Montgomery Scott, the chief engineer of the enterprise. And in his future, he would just talk to the computer, which is essentially that colorful looking screen. There'd just be a voice interface, and he'd just tell the computer what he wanted. So he might, if this were in a chemical engineering context, he might just say, "Hey, computer, I need to separate propane from 13 tons of NGL liquids. I want to have a liquid propane product at the top." The computer would just click and whir as they had depicted computers back in those days, and say that, "Hey, you're going to need a column a little under 2 meters diameter, but 1.65, 1.7 meters in diameter. I'm recommending 20 valve trays so you can turn down properly. This is your condenser. I'm going to recommend a particular condenser, maybe a chilled water or a cooled water condenser with this duty." And being in Star Trek, they'll actually be able to fabricate that computer. So this is somehow, sometimes people have an image that the computer is going to be able to solve problems for them. Yeah, and again, I like to stress that these software applications, again, are just tools. Just like a spreadsheet is a tool. And the spreadsheet won't make someone an accountant. You need to fill it in, and you need to put the correct rules and math, and set up your problem and interpret correctly. So this is, I call this one of the fantasies that sometimes we have about these computers. Now, before I set up this company, I used to work for a couple of software outfits. And one such company was a company called Hypertech, and they wrote software. And one of the software applications they wrote was HYSYS.
Yep, I see.
Okay. So this is, when I was working in this company, I started off as a graduate engineer working in tech support. So I'd be on the phone support. I'd be the guy that answers all of your calls. And this is an actual call that I had gotten. And it goes like this. I pick up the phone and say, "Hey, how you doing? You reach tech support." And I would get a typical response. And this is a response I get a lot these days as well when I'm sometimes if I'm teaching simulation classes. "Your software doesn't work. Got problem?" And I'd respond, I'd ask them and say, "Hey, I'm really sorry to hear that, but what kind of problem are you encountering?" And the problem that we're seeing is my senior engineer inputs some bad data into the simulator, and it calculates, and it produces bad results. And this is when you have to start, this is when typically I'd start reaching for the for the Panadol and painkillers, because I know this is going to be a long call. And why wouldn't your engineer want to put good data in the first place? And sometimes the responses I get for this are you implying that my engineer is dumb? He's got a PhD. Why doesn't the software just tell him what information he needs to input? And I'm thinking that, hey, if the software could do that, wouldn't that put him out of a job? So we go to engineering school for 4 years for a particular for a reason. Yeah, and it's not input data into simulation software tools. There's quite a bit of thought that needs to go on when we're setting up a case, when we're setting up our analysis, or setting up our computation, and we're setting up a simulation environment to address this. Yeah. So now, yeah, and you've got that age-old the age-old saying, garbage in, garbage out. Yeah. So you need to be careful about what information you feed into your software application or your tool or your spreadsheet. You need to make sure things are properly defined and well prepared. The data that you put in needs to be validated data. If you're taking a look at information from your data historian, you want to make sure that the instruments are properly calibrated. The instruments are on. Yeah. Okay, so when do we use simulation tools? Where do we use what aspects of our work do we start using simulation tools? Well, if I take a look at an asset, yeah, any kind of asset, a platform, a refinery, gas plant, petrochemical facility, it typically goes through the following life cycle. So I'm showing here some of the various phases for an asset and typically some of the types of computations that you perform. So the first thing that happens is you typically come up with a new opportunity. And with this new opportunity, you generally have to conduct some form of feasibility studies or conceptual design to come up with perhaps some a pre-feed type detail. Yeah. Once you've come up with this new opportunity and done some conceptual design, concept select, then you generally go through some kind of a basic engineering or front-end engineering design, where you'd be looking at equipment sizing. You'd be taking a look at some preliminary operability of the system. After that, you might be looking at detailed design, where you want to start taking a look at perhaps some of the transient behavior, because you want to take a look at controllability in addition to the operability of your system. You typically go into construction, and typically at this phase, when your facility is starting to undergo construction, you might use this period to start training your operators. You then do some commissioning and startup. At this point, the commissioning and startup, you generally would have some process support where you're taking a look at troubleshooting certain issues. At operations, once your facility is up and running, you might be looking at performing some, looking at some performance operations, so some performance monitoring, some optimization, planning, debottlenecking perhaps. Yeah. And at some point in time, you might be looking at extending or revamping your facility. If you're operating like an FPSO, a floating processing, storage, and offloading facility, you may be looking at demobilizing it from one field and using it, commissioning it for another field. And in some cases, you would look at decommissioning the actual facility. There's some things that you might have to do, flushing out, flushing, cleaning, etc. So at all of these phases of the life cycle, you are going to need some form of computation or simulation. Yeah. Now, what kind of tools and software applications do you have there? And I always get people coming up and asking me these questions. What kind of software applications do I need? Well, let's take a look at some of the typical activities that you're going to be doing. Yeah. So if you're a process engineer, if you're working for a design company, or if you're working for a technical services group, you'd probably be looking at generating heat and material balances, taking a look at flow rates, operating conditions, taking a look at vapor liquid flows, partitioning of components in these various vapor liquid phases, reactions, etc. If you're somewhere upstream, you might be looking at multi-phase pipeline type of analyses, steady state or transient analyses like flow assurance type computations, slugging, wax formation, hydrate formation. If you're downstream or even upstream, you're going to have a flare system. You want to be taking a look at the design, flare header design, flare stack design, header design, etc. Heat exchangers, you're definitely going to be looking at heat exchangers, shell and tube exchangers, air coolers, etc. So you have all of these tools. You've got all of these applications and all of these tools set up. And what software should I use? Yeah, that's a question that always crops up. What software should I use for these types of applications? Because there are so many different applications out there. Process simulators, for example, you've got for flowsheet simulators, you've got HYSYS, Unisim, Aspen Plus, Pro 2, ProMax, Symmetry, VMG Sim, etc. Yep. You'd be wondering, hey, is one software better than the other? Is HYSYS going to be better than Pro 2? So in the early days, one of the things that I used to do is, in addition to doing tech support, I used to sell software. And I'd be the guy that tells you, buy this application, buy HYSYS, it's better than Pro 2. Or when I used to work for SimSci, I'd say, hey, Pro 2 is better than HYSYS. Because as a salesman, as a software salesman, I had three objectives, three main objectives. And my three objectives were make the most commission that I could make the most commission I could make, and make the most commission that I could make. So you need to be careful when you're listening to salespeople, and you need to know exactly what kind of software application you need before you actually before you actually start looking at or evaluating or buying any software. Yeah, so you need to be a bit careful there. Now, I'd like to run through a couple of examples over here and just show you some of the pitfalls that you may encounter when you're performing simulation computations on whatever software application you're using. And these examples that I'm choosing are process engineering type computations. Yeah. So sometimes you get a piece of software or an application and you say, hey, this software is really great. It calculates really, really fast. Yeah, and I think the early days, HYSYS were like that. Compared to Pro 2 and Aspen Plus, it was super fast because the way that the architecture was set up, it was calculating while you were typing. Yeah, it had this fancy event-driven type of engine where you start typing information in, and whenever it could, it'd start calculating and flashing the stream. So it's great. It calculates really fast. Well, let's take a look at this. And this is one of the examples. Actually, if you've taken one of my classes, this is one of the examples that I typically use for an exercise. And in this case, what I have is a gas dew pointing unit. Yeah. So gas, I have a rich gas coming in a gas exchanger, and I'm chilling that gas in the chiller, separating the vapor and the liquid. And then I have some heat integration. I'm recovering some of the chilling in gas exchanger. Yeah, so I've got two exchangers there, gas heat exchanger and a chiller. So before I want to go on anymore, one of the things I want to do is I want to understand what's the dew point pressure of the LTS vapor stream at minus 20 degrees Celsius. Yeah. At what pressure does the first drop of liquid appear? So if you're a HYSYS, Unisim, PetroSim, VMG Sim, Symmetry user, the way you would do that is you'd obviously punch in a vapor fraction of 1 to indicate your dew point. And you punch in a temperature of minus 20. And the software will tell you what the dew point pressure is. So in this case, based on this, it tells me the dew point pressure is about close to 30 bar, about 2,962 kPa. And that would be your answer. In this case, it would probably be true, but there's one thing that you probably want to have a look at. And that thing that you want to look at is the phase envelope. Let's take a look at the phase envelope of this fluid, of LTS vapor. So I would generate the phase envelope. And that's an easy thing to do. If you have a simulator, you just click on the tab and then choose a stream and generate your phase envelope. So I've got, if you can see over here, I've got two lines, a red line and a blue line. The red line is my bubble point line, and the blue line is my dew point line. So if I take a look at my location, my dew point location at minus 20 degrees Celsius, if I'm at minus 20 degrees Celsius, then the, can I put on a, hold on a sec, let me try and figure out how to put my pointer. There you go, got my laser on. So at minus 20 degrees, my dew point is somewhere around there, about 30 bar, yeah? So that looks correct. However, here's the thing though. If I take a look at the entire phase, I actually have two dew point pressures, one at 30 bar, and this other dew point pressure, which is at 80 bar. Now, I see this because my phase envelope has this rather strange behavior. Yeah, I have this bulge. And this bulge is what we call the retrograde region. So I actually end up having two dew points. I've got, this is what I might refer to as a dew point. And this point over here is what I might refer to as a retrograde dew point. Yeah. So if you really want to take a look at your fluid, it's really important not just to do the flash calculation in the simulation tool, but you need to also go and plot your phase envelope. So this is another problem that I typically get. My distillation cannot converge. Yeah, I think if I had like 1 ringgit for every time I heard someone say this, I think I'd be extremely rich. I wouldn't have to work. My distillation column cannot converge. So what do? I set it up, and then what happened when it didn't converge? I press reset and then I run. I press reset and then I run, and it still doesn't converge. And then what doesn't happen? Then I'll change the specs. So let's take a look at one of these examples. Okay, so I've got like a simple depropanizer model here. And I have a reboiler and a condenser. Now, after putting this in, after putting all the specs in, the pressure profile, I have two active specifications, reflux ratio, and then overhead propane fraction, overhead propane mole frac, yeah? So it's a depropanizer. I'm essentially taking out propane in the overhead, and I have the heavier components, butane plus, coming out as a liquid product. And you can tell that this is yellow, meaning it's not it's not convergent. Yeah. So normally this will happen. Now, what I would typically advise in a situation like this is let's just take a look at the material balance before actually going into the distillation column. Let's look at the material balance. So over here in this page, I have the material balance, and this is just a simple case over here. So I'm putting things in kilogram moles. So my feed, I have methane, ethane, all the way up to normal butane, and this is my composition. Now, the first thing that I do before I start the simulation is I'm just going to do a very, very simple material balance. It's a depropanizer, so my propane is going to go at the top, and my butanes plus are going to come down the bottom. So I'm just going to do something simple. I'm just going to draw a line between that and say, okay, propane go at the top, butanes go down the bottom. Now, and I know what you're thinking. Said, hey, if you're still in school, and I noticed some of our old interns logged in over here. So some of our interns are going to be saying, because they've just sat for the distillation class, they're going to say, hey, Rafil, that's not going to happen. You're not going to get a perfect separation there. You're going to get some light key going in the bottom and some heavy key going on the top. You absolutely will. But in this case, just humor me. Just draw a straight line between your propane and isobutane. Notice I've also arranged these components with regard to the boiling points. So I'm just doing like a simple dumb material balance. I could use a calculator and a pencil for. So after I've done this, I calculate everything that's going to the top and everything that's going to the bottom. So I have a total feed coming in of 141 kilogram moles and 105 going over the top, 35 coming in the bottom. So I can also take these flow rates, component flow rates, and I convert them into mole fractions. And lo and behold, if I take a look at this, if I send all of the propane to the top, and it's not all going to go to the top, as we know, you'll get some in the bottoms. Even if I have some kind of a perfect separation, even if I've got like some kind of like a nanobot grabbing all of my propane molecules and chucking them over the top, the maximum I'm only going to get is about 35% propane. Yeah, 0.35 frac. And this is what I've asked for, 0.95. So no matter what I do, if I just keep on hitting run and reset, I'm not going to be able to converge this column because I will never meet this requirement. Yeah, I'll never be able to meet that requirement. So it's absolutely imperative to run a quick material balance before starting to do any kind of specification for your column. If any of you have been in the in my distillation class, you'll see that I do something step by step. In fact, if you've watched me troubleshooting a distillation problem, first thing I do is a material balance, something like this. Figure out what goes on the bottom, which goes to the top, and then I would look at performing a quick flash calculation to estimate temperatures. Yeah. So it's absolutely imperative before we do anything, do material balance first so we know what's going to happen. So in a situation like this, putting a 35% or 0.35 mole frac, a 0.95 mole frac is not feasible. Maybe the spec for this should have been recovery, 95% recovery of propane at the top. Yeah. So again, this is just an easy thing that could be very easily flagged if you did a material balance first. Okay. So now what I'd like to do is I'd like to go through what I call these 10 commandments of process simulation. Okay. So number one of the first recommendation that I'd like to make over here is before you start your simulation, before you start firing up your software tool, before you're going out placing an order for software, the first thing that you need to do is understand your objective and define your objective. What is it you want to do? Are you having a hydraulic problem in your distillation column? Or are you having a problem with your control system in your distillation column? Are you having some problems with compressor controls? Are you surging a lot? Are you finding that you're getting a lot of slugging in your pipeline? Because you need to identify an objective. The reason for that is there's not one single mathematical model or there's not one single physics model that can represent the behavior of all fluids and all processes. You're going to need to use various tools. That's why in the early one of the slides, I was talking about process flow sheeting tools like HYSYS, Unisim, Symmetry, flow assurance tools like Olga, LeaderFlow, or other applications. Yeah, so depending on the type of computation you want, you're going to have to depending on the objective, that's going to determine the kind of computation that you're going to need. Yeah, so you need to be able to identify that correctly. The next thing that we're going to look at over here, second point, is hold on a sec. The second thing I'd like to recommend is identify your system or process. Now, I always recommend sketching your process out by hand. Now we work with a lot of PFDs, PNIDs, PFS, different kinds of drawings, and we need to convert. We're using the information from the drawings to build our simulation models. Now, some of these drawings tend to be rather complex, and in some cases, let's say, for example, if I'm building a steady state simulation model, I may not need to model certain bypass lines or recycle lines or drains. So it's really important to first identify the system or the process that you want and sketch it out. I recommend sketching it out by hand. I guess these days you could either sketch it out by hand or you could use any kind of a drawing tool. I see a lot of people using Microsoft Excel for these kinds of things. Yeah. I think also by sketching things out by hand, you also get very familiar with the processes quickly. The next thing you need to know is, that I recommend you do, is to draw an envelope around your system. Yeah, identify all the in and outgoing material and energy streams. In some cases, some people forget that there might be recycle streams. And when you're doing your material balance, you find that your one of the streams is you're getting more flow than what you're putting in. So you make sure you know what your boundaries are and where you're drawing those envelopes. The next thing, number 3, it's really important to imagine what's going on physically. Now, one of the things I'd like to say is most engineers and scientists need to have really great imaginations. You need to be able to describe the mechanisms behind the systems or the phenomena that you're studying. Even more so when you're doing chemical engineering type problems. In some cases, you might be looking at systems like azeotropes. How do you imagine an azeotrope? If you have like a high boiler, for example, a high boiler where you have a heavier component boiling off before a lighter component. Yeah, why does that happen? Well, one of the images I have for a phenomenon like that is the heavier component might be a certain size molecule. The lighter components might be smaller. However, under certain conditions, we might be having things like hydrogen bonds or some form of attraction, which are causing these smaller molecules to clump up and form pseudo molecules. And these clumps may be bigger in size than your heavier component. Therefore, at certain conditions, your heavier component may tend to boil faster, while these smaller components are in some kind of a clump state due to the hydrogen bonds. So these again are just like kind of cartoon images that I sometimes use to help me visualize what might be going on. One of the things that I find sometimes when I'm going to the universities and talking to students or giving like a workshops in the uni is I find the following, and I definitely used to be guilty of that as well, is that we, as a student, sometimes we tend to start memorizing equations and regurgitating them during our exams. Now, it's really important to not just do that. It's easy for me to say now that I don't have exams to cram for, but it's really important to really understand what the underlying mechanisms are. Yeah, if I'm doing like a polymerization and I have like a single site versus a multi-site reaction, what is going on? What's happening? If I'm taking a look at designing a catalyst, or if I'm taking a look at the kinetic expression for a particular reaction, what is the rate determining step? Do I have any transport or mass transfer limitations? If I'm designing a catalyst, I need to imagine I've got like a component coming in from a bulk phase, getting onto the surface of my catalyst, going through the pore, going to the active site, undergoing some kind of conversion or reaction, and then getting back out to the bulk phase again. So I can, imagine that's going on, and then based on that, I can figure out what kind of mathematical model or tool I need. A transport phenomena, Fickian diffusion, or a kinetic reaction kind of framework. Yeah. So it's important to imagine what's going on physically. Sometimes you need to model a particular piece of equipment. So I think one of the early pieces of equipment that I had encountered in my as a graduate engineer is a liquid ring pump for vapor recovery. I didn't know what that looked like. I didn't know how it worked. Fortunately, these days you got YouTube, and surprise, YouTube has more than cat pictures. So I could just go Google, search on YouTube, liquid ring pump, and I could actually see a Nash pump. Nash, the manufacturer, actually has some nice animations of how their pump works. So there's a lot of things that we can find out, a lot of resources that we can use to imagine, to give us a picture of what's going on physically, if we're not actually in the field, or if we don't have a piece of equipment in front of us. So that's actually, I find that pretty critical. Okay, the fourth thing that we need to look at over here is, once we have taken a look at the type of phenomena that we're studying, the type of phenomena, it's really important to then kind of figure out what kind of physics or mathematical model that we need. So one of the things we do, if you just take a look at our a typical chemical engineering curriculum, we've got thermodynamics, transport phenomena, reaction engineering, process controls, and economics. And all of these subjects come with some form of physics or mathematical model. Yeah, it's important for us to take a look at the kind of phenomena that we're studying and understanding what kind of underlying physics and physics models we need. Now, if I'm looking at a distillation column and I'm using a flow sheeting tool like Symmetry or Unisim or HYSYS or Petrosim, these tools essentially take a look at distillation columns from a thermodynamic perspective, a vapor-liquid equilibrium. You'd specify they perform heat and heat mass energy balances around your column. Yeah, the impact of mass transfer in general is not taken into account. You do have some specialty columns which have mass transfer, but these are not very commonly used. Most of the columns that you're going to be encountering and using for your day-to-day work, if you're in oil and gas, are generally going to be equilibrium columns. So these columns are only going to be looking at equilibrium effects. They're not going to be taking into account mass transfer effects, meaning you're going to need to compensate by taking a look at efficiencies and tray efficiencies. Yeah, so it's really important to understand what kind of physical phenomena is taking place and what kind of models you need. The next thing you need to do is, once you've identified that, you need to figure out whether the software application that you're evaluating has those models. So if I wanted to, if I'm working on a job where I need to troubleshoot hydraulic problems in a column, I need to make sure that the software tool that I have is going to be able to do hydraulic computations, tray design or tray rating. I need to be able to come up with a look at a tool that tells me what is my operating envelope for each of the trays. I needed to identify a situation where I might have high vapor flow, which might result in entrainment, or low vapor flow, which may result in weeping. Yeah. So it's up to us to identify these requirements and to make sure that the software applications that we have cater to these requirements. Okay. The next thing I'd like to say is number 5, know your components. It's very, very critical. Know your components, understand how they're going to be interacting with each other. Now, when you know this, then that'll give you an indication of what kind of property estimation method you're going to need. So if you're looking at, say, for example, a sour water stripper, if you take a look at a sour water stripper, you've essentially got sour water, which contains hydrogen sulfide, ammonia, and some other components that it may have picked up from various processes. These components, hydrogen sulfide, ammonia, they're not going to be staying in that molecular form when in the water. They're going to essentially be dissociated into ionic or electrolyte forms. So when you are modeling a system like that, you can't be using your standard cubic equations of state, which are for non-polar molecules. You may need to use some specialty package or an electrolyte package. If you are modeling a depropanizer, like the example that I gave before, the components that I had, methane, ethane, propane, butanes, pentanes, etc., those are non-polar molecules. Those are well handled by an equation of state, a cubic equation of state, like Peng-Robinson or SRK. Yeah. So it's really important to understand the components in your system and how they're going to interact with each other, and what kind of interactions you want to be able to model. Now, here's a really interesting case here, where the solution is a bit counterintuitive. So I know this from some of the names, some of the attendees. Some of you guys are coming from oil and gas. You might be coming from an engineering company or an operating company. If you're in oil and gas, one of the things that you're typically going to do, or you'll be concerned about, is hydrate suppression. So if you're using a tool like a standard process simulation tool like Symmetry, Unisim, HYSYS, you have the capability to model hydrate suppression. And that function is generally going to be embedded within a cubic equation state like Peng-Robinson. Yeah. So if you're using a HYSYS or Unisim, it'll be within Peng-Robinson. And you would essentially take methanol or MEG, TEG, and then you would add that to your wet stream, and then you would be able to take a look at the hydrate suppression capability. When you calculate your hydrate point, you'll see that it gets suppressed. So you'd use a cubic equation of state to handle this. However, if you were taking a look at manufacturing methanol or MEG or MEG, and you're taking a look at the reactions to manufacture this and the separations, yeah, to separate the purification, you can't use a cubic equation of state for that. So if you're from the methanol plant, any of the methanol plants, if you're modeling your methanol reaction and purification, you would have to look at an activity coefficient model, like a NRTL or something like that, to handle the liquid phase activity. So you don't always, you might be looking at the same molecule, but because you're looking at different kinds of behavior, the synthesis of methanol or a glycol versus the utilization of one of these alcohols or glycols for hydrate suppression, you'd have two different types of property packages that you need to use for that. So it's really critical to know exactly what kind of phenomena you're interested in. Yeah, what kind of components and what kind of phenomena you're looking at modeling. Okay, number 6. This is something that's pretty critical as well. Know the context of your feed stream. Know the context of your feed, so you know how to characterize it correctly. So one of the things, one of the common things that we look at is taking a look at the hydrocarbon compositions from upstream analyses, or maybe even like downstream or midstream. Typically, if you think about it, most of your hydrocarbon compositions are obtained, are determined using a GC, a gas chromatography unit. Now, the way a GC works is you put in your sample, and it separates, it determines how long each molecule stays within the apparatus. And when it comes out, there's a detector. Now, the thing about the GC is the feed, the sample has to be dry before it goes in. So you take all the water out. So if you take a look at the GC analysis, it's always going to be bone dry. There's not going to be any water. So you need to recombine. So you need to understand how much water to put in. As a minimum, you would probably want to saturate that hydrocarbon stream at the sampling temperature and pressure. Maybe, yeah. So you need to know the context of that sample or that feed, because you may have to perform some computations to treat it or to do some kind of recombination to make sure that you have the right compositions. Another thing is you might be given separate gas-oil ratios, gas composition, oil liquid composition, water cut, and you might have to recombine that before performing your simulation. So how you do that, there's no one way there's not a single way to do that. It always depends on the context of the feed. Where are you getting that composition from? Where's the sampling from? What temperature and what pressure? Yeah, so it's really critical to understand that in order to characterize the feed. And you're going to realize one thing, though, that sometimes that is actually one of the most important things that you need to do. Defining the components, properly packaged, and characterizing the feed is absolutely critical, because if you miss out on that, the rest of your simulation is going to be practically useless. Yeah. Once you've got your feed properly characterized, all the simulation is going to do is it's going to flash it at various temperatures and pressures across your process. So the critical part is actually getting the compositions correct. Next, number 7. This has to do with compositions, components as well, and this is something I like to do. Know your component boiling points. If you're using a simulator, you can always go to the property package and figure out what the boiling points are from there, or there's a lot of places where you can look them up. It's absolutely critical to know what the boiling points are, and what I like to do when I'm doing my analysis is I like to arrange them in terms of boiling points, because then I can kind of like say, okay, I can partition things roughly by hand. Yeah. So if like the example that I gave for the distillation column, it's a depropanizer. I arrange all the components in boiling relative to the boiling points, and I can say, okay, propane lighter, go to the top. Yeah. However, you need to be a bit careful, because if you might have water or azeotropes, hydrogen bonds in your system, that may throw things around a little. So you need to be a bit careful there. Yeah. Okay, the next thing, number 8. And this is something pretty critical. So if you worked with me before, you'll know that I'm really particular about defining the units of measure. So even if you come by the East 101 office and you take a look at all the whiteboards that we have, if anyone has a number, there's always going to be a unit defined, because it's really, really easy to mess up by making by unit errors, by working in different units. Some of the common pitfalls that we find are sometimes absolute versus gauge for pressure, standard versus actual flow rates, and utilizing constants, a gas constant. Yeah, so the gas constant is a function of the units. The value of the gas constant is determined by the units that are used for temperature, pressure, volumes, etc. So make sure that you keep track of all the units. In school, we have to do that unit equation. Make sure that you always have that in, because these errors can be quite deadly. Yeah. But they're very easily, very one of the most easily avoidable errors. Yeah. Okay. Number 9. As I've mentioned, I guess several times, it's absolutely critical to perform a simple material and energy balance first. Yeah. So if you work for a big company, a big engineering company or an operator, most of the time you have simulators. You probably have more simulators than you can shake a stick to, or you have licenses or things like that. When you're with a small company, you don't always have access to a simulation license or simulator license. So what we typically do before actually having to put something to run a simulation is we do like a hand calc first, a simple heat and material balance, yeah. Or sometimes you would use, if you go, if you look on the internet, you can actually use or buy very cost-effective flash routines, like the National Institute of Standards. They have something called RefProp or something, and I think it's about $200 US or less for like a flash engine. So you can use that to do simple heat and material balances, flash calculations. Even if you didn't have something like that, you can just use Antoine vapor pressure correlations to take a look at vapor pressures and do simple flash calculations. So it's important before actually doing something very complex, or even maybe before investing in and buying a tool, to just do like a simple heat and material balance first. Yeah. So if you've taken my distillation class, you'll find that first thing that I do is do a quick material balance using the component splitter, and then do a quick flash calculation at the top and bottom. Yeah, a dew point or bubble point flash at the column pressure to estimate temperatures. So these are simple things that you can do on your simulator as well before actually doing like a rigorous distillation. So this is critical, these simple material energy balances first. And you would use that to essentially come up with two things. One is when you come up with a simple material energy balance, that means you would have given your computational process some thought. And when you're doing things by hand, you tend to keep track of things a lot better. If you plug things into a simulator, sometimes you lose track of things, and you might get simple errors by misplacing a decimal point. So instead of 1,000, you might get 1,000,000. If you do a hand calculation first, you would at least be able to do some sanity checks or order of magnitude checks first. Because once you get into the simulator, sometimes things go really fast. You start plugging things in, and the simulator calculates really, really fast. Or at least they do these days. Okay, so finally, the last thing. What's the top thing that I'd like to recommend here? Plot your phase envelope. Yeah. It's really critical to plot your phase envelope. I think if you go to a lot of the chemical engineers, some of the senior engineers, guys like in their 50s or 60s, you walk over the cubicles or their offices, and then you'll definitely see like a phase envelope stuck up or pinned up. And the important thing is you will be when you want to work with a fluid, you can't always know what's going to happen if you're just looking at a PFD or a PNID. You want to know how the phase is going to change across your process. Yeah. So if I'm looking at, say, for example, like a compression train, I want to make sure that the suction to the compressors is going to be all vapor. I want to make sure that there's no liquid in the compressor suction. If I'm looking at a pump system, I want to make sure that the liquid feeding into the pump is a subcool liquid. So if I had a phase envelope, I can actually see where in the phase envelope this fluid would lie based on the temperature and pressure. So that's absolutely critical. Yeah. So that brings me to the end of my talk. So we've gone through some of the common practices, simulation practices, some of the common pitfalls that we would typically encounter. And I thank you very much for coming online and participating. I see we've got like maybe over 70 people. That's a good crowd for a Wednesday afternoon, Wednesday evening. So I'd like to thank you all for logging in and listening into this webinar. I appreciate that. What I'm going to do is I'm going to hand over to Zihong, and we'll give you a bit of information, and we'll have a question and answer session. Yeah. So thank you all very much, and stay online, and we'll get to the question and answer session.
Thank you, Rafil. Thank you for an insightful and entertaining session. And everybody, thank you again for attending the webinar all the way to the end. As Rafil said, the Q&A session will begin soon. And we'd just like to take the opportunity to remind you that we have the next East 101 webinar where the topic is analytics and machine learning in the oil and gas industry. And the speaker will be Dr. Anwar Hamid, who is our East 101's process engineering manager, who has been invited to universities to speak on this topic as well. And the date for the webinar is 3rd of June, which is 2 weeks from now, as next week will be Hari Raya week. And the time is 4 to 5 p.m. Malaysian time. Please, for any further questions, you can contact myself or Avinash and at our numbers and our email, and also go to the website at East 101 to view the recording of the webinar once it is uploaded. We can also follow us on LinkedIn to keep up to date with any of our other activities. Just a quick reminder for the Q&A session. To keep things organized, I think we kindly request for you to stay muted and type any questions you have in the chat box. And we will read it out to Engineer Rafil. The question is, how do we know whether an assumption is a good one when we don't have sufficient data at the time?
That's a very good question. How do I know that my assumption is a good one when I don't have any data at that time? So this is where I guess you need to start developing the capability to make guesstimates. I mean, if you were to ask me, and it would really depend on the type of assumption that I would make. So the first thing that I would probably do is take a look at the system that I'm studying and correlate that to some physical model that some kind of a mathematical or physical model that I can kind of use to make a guess. Let me come up with maybe one example. If I'm taking a look at a particular system, say for example, I have a tank, and I need to make an assumption on the amount of inventory in my tank. Yeah, amount of gas inventory in my tank. Let's say it's predominantly a gas, and this is kind of a simple thing. Yeah, if I know, if I'm going to the field, I see a tank in the field, and I want to know how much inventory is in that tank, and all I have is a pressure gauge. I'm going to need to make some form of an assumption, and the first thing that I would probably do is use the ideal gas law, PV equals nRT. I look at the pressure. If I don't have a temperature reading, I might have a temperature gun and just shoot the outside, and then assume that that's going to be the internal temperature, and then I would use that as my assumption. Yeah. So it's a very interesting question, and it really depends on the particular situation that you're looking at. Now, I participated in some advisory for final year projects, and one of the questions that I get is, I don't know what the reaction mechanism is. I don't know what the kinetic parameters are, and I need to size my reactor. Yeah, but I don't have this particular reaction set. So I'm going to make an assumption. How are you going to make that assumption? Well, let's say if I don't have that particular reaction mechanism for those particular components, what I might do is look for something similar as possible. And by similar, I mean I'd be taking a look at molecular, either a molecular structure, functional group, or reaction mechanism, substitution, ring opening, or something like that, for something similar, and state that assumption. Yeah. So that's what I would do in a situation in these various types of situations. So it's a tricky thing, and it really depends on what kind of situation you're in to determine whether or not your assumption is good. Easiest thing to do is also could also be find someone that's done it before and ask them. That's something that I've done as well. There's a lot of really smart people and experienced people out there that have done and seen a lot of things. Yeah. So if I'm in a bind, I got a bunch of buddies out there. I think some of these buddies are even logged in. Some of the guys that I see here can probably do one of these webinars. We might invite him to come and do one of these webinars as well. So that would be my response. And I know it's not a very definitive response because there really isn't one single way to do this.
Thank you, Rafil. Thank you very much. We have two more questions, and the
Okay.
first one comes from a Mr. Amin Rosalie. Sometimes the project schedule can be a constraint to implement the 10 commandments of process simulation. Any tips on how to deal with this situation?
So what do you do when you were working for us? I mean, well, here's the thing. When you talk about time constraints, let me give one example, okay? So one of my I was doing some work and for a company, and one of the engineers comes up to me and says, "Hey, I'm trying to converge this crude tower. Yeah, I'm trying to converge this crude tower, and I've not been able to do it for the past 2 months. I just can't converge it. And can you help me?" So I took a look at that, and I went through some of the steps. One of the commandments, which is do a heat and material balance. Yeah, material balance first. If I have a crude tower, I know what is my crude assay, my TBP crude assay. Based on that, based on the crude assay, I know what my boiling point range is. I can estimate what liquid volume fraction I'm going to expect for each of the products. So using my crude, my TBP curve, I can either graphically estimate what my product yields are going to be, or if you're using one of these fancy tools, if you've got about like 40 to 50 grand US in your bank account, and you can lease a software kit, it actually does that automatically for you. So I'll note down what the product yields are. I know what the boiling points are, so that gives me an idea what the temperature ranges are, and I use those as initial guesses in my crude tower, and I can guarantee you it's definitely going to converge because that's the information you're putting in is already your solution. So that took me 15 minutes to do. So in some cases, if quote unquote shortcuts, i.e. just banging, running in and doing like a rigorous column without doing all these pre-calcs, actually you end up wasting more time trying to figure out what's going on. Having this pre-calculation or initial calculations might end up actually saving you a lot more time. Yeah. Now, I'm gonna admit sometimes if I have a problem, if I'm given a problem, first thing I do is I try banging on it. It's just like this now. You buy a new piece of electronic equipment now. You buy a new cell phone. Yeah. First thing you could do is you're going to start using it. Yeah. You'll start using it. And then when you come across a problem, then you're going to spend some time. You're trying to figure out how to do something, how to use a messenger or something like that. When you come to a problem like that, then you only open up the manual and figure out what's going on. Same thing for me as well. Sometimes I might jump into a problem and literally start monkeying about without actually knowing any of the physics or anything around it. Now, if I find myself doing that for like half an hour, then I make myself stop and I go back and take a look at some of the fundamentals and then attack the problem. Yeah. So I think if you take a look at those steps, I don't think it takes much time. In fact, I think it's going to save you time. I mean, okay.
Thank you, Rafil. So the next question up is from Mr. Nishant. And the question is, when we have immiscible liquids like water
Yeah.
and hydrocarbons, organic hydrocarbons, can you comment on how do you approach a simulation when we do not have real binary interaction parameters other than those estimated by the simulator itself?
Okay, that's a good question. And if you take a look at what's available now, and this is a very tricky problem, because there isn't any there isn't any one good way to do that computationally. Yeah. So just if we take a look at that phenomena of the situation where you've got water and organic components, a couple of things can happen. One, you can have like a nice separation. Another is you might have obviously some organic component in the water and vice versa, oil in water or water in oil. And you could also have situations which are sort of like mechanical or surface chemistry related, like colloids, emulsions. Yeah, none of these things are properly estimated in the simulator. Yeah, if you're using HYSYS or Unisim, I'm not sure what symmetry is doing, but I would take a gander that it's going to be similar. If you're using like a cubic equation of state, the amounts of, say, for example, oil in water. If you take a look at the oil phase, you'll find that you do have a bit of oil in there. It uses this kerosene solubility correlation based on kerosene in water to estimate how much hydrocarbons are going to go in. So there really isn't a good way to perform this computation. The only thing that we do is to take a look at plant data. Say, for example, if I want to take a look at these sort of carryover entrainment, I would take a look at compositional analysis or oil in water analysis from the plant, and then I would do some entrainment calculations to force that that in, yeah, with the simulator. So you would need to have some form of what I would recommend is, in this case, you would need to have some form of field readings or field lab results to get this done properly.
Okay, thank you. So we have another question coming in from Chiu Chi Wei. Question is, for estimating binary interaction parameters of created pseudo components, some binary interactions don't show up. What might be the possible reasons for that?
Okay, so I'm going to assume, let's say you're using a Peng Robinson, for example. Yeah, and this is a very interesting question, and there's some very interesting ramifications with regards to this. So with regards to binary interaction parameters, if I take a look at a cubic equation of state like Peng Robinson, you have the Kij parameters. And the Kij parameters essentially act upon the attraction term, the Ai and the Aj. Yeah. So they strengthen or they weaken the attraction term between these components. I'm not sure what software application you're using. If you use Pro2, SimSize, now it's, I guess, owned by Aviva. At least back when I was working for them in the 90s. In Pro2, if you add a hypothetical component, pseudo component, and you're using like a cubic equation of state like SRK, you look in the package, it'll show empty or zero for the pseudo components. It does not add any. It does not add any of the interaction parameters. Why? Because it does not do any kind of estimation. So let's put that aside. If you're using HYSYS, and if you're using Peng Robinson, for example, cubic equation of state, if you put in, if you're modeling like an upstream case, I'm assuming again, I'm going very specific in this case. If it's an upstream case where you have ethane, methane, ethane, propane, butanes, let's say alkanes, yeah, paraffins, and then you add like C6 plus type components, heavier components as hypotheticals. You'll find that the HYSYS simulator, HYSYS, Unisim, Petrosim, and Symmetry, they will put non-zero or non-empty interaction parameters in the Peng-Robinson equation. And what they do is they have like a correlation to estimate what these values are. Yeah, so they would essentially estimate these particular parameters. Now, what's better? Is Pro2 better that they don't estimate? Meaning if they don't estimate, then you need to go and put it in yourself, or you estimate. What's better? So it actually depends, because if you want to have some good, if you really want to have a good estimate of what these interaction parameters are, then you need to do some form of tuning. Yeah, you need to do some tuning to tune the interaction parameters. So if you look at a tool like a Pro2, what you would do is they would not have any interaction parameters, they'd be empty. So what you do is you would put in your initial gas, and then you tune it based on field data, like a gas-oil ratio. So you target the gas-oil ratio, and then you manipulate those interaction parameters for the hypos until that matches. Yeah. So if you're you see that we have some tools, or there's some built-in tools in the property package which allow you to manipulate these interaction parameters. Yeah. So in some cases they calculate it, some cases they don't. It really depends on the software application that you have. However, if you really want to have like a good level of accuracy or resolution, you need to tune those interaction parameters. So if you're using, I think HYSYS, there should be something in the ComThermo that you do. Pro2, something Pro2, Symmetry, you can use the optimizer or the adjust to modify and tune these interaction parameters. Yeah. So sometimes they'll show up, sometimes they don't, but at the end of the day, you need to make sure that there's some numbers in there, and you need to make sure that they're tuned. Okay,
All right.
That's all I have for that.
Thank you, Rafil, for your very detailed answer. We have one more question coming from Mr. Satish Kumar Kalluri. The question is, are there any good proven simulation techniques or software solutions to arrive at compatibility between crude oils? Although I know solubility-based correlations is one method to loosely estimate compatibility.
I'm not sure what we mean by compatibility between crude oils. Would it mean compatibility meaning that it would give me the same kind of product yields, perhaps? Does not produce layers. I see. By layers meaning that, okay, that I believe would be a function of your densities, right? It would be primarily a function of your density and potentially viscosities, perhaps. I'm thinking. I'm not sure exactly what kind of software applications may handle this. I'm guessing. See, the thing is, here's an interesting thing. In which you'll notice, if you take a look at a tool like, I'm going to use it. Okay. I'm going to use the term HYSYS family to represent HYSYS, Unisim, Petrosim, because they're kind of written from a similar framework. Yeah. If you use any HYSYS family software, You might find in certain situations, if you add like two types of hydrocarbons, you might find them splitting into different liquid phases. Now, whether that is actually no indication of if that would actually happen in reality. What it does is these software tools separate things by density differences. Yeah. So if you have like a very heavy crude with a lot of asphaltenes, and the densities were its density is very high, close to water, and then you had like maybe like a medium crude, you might actually see these splitting up into two different phases, but that is two different liquid phases, but that is not indicative that that might happen in reality. So the answer to that is, I think most of your flow sheet simulation tools will probably not give you a good indication. Yeah, I think you would probably have to rely on some kind of a correlation or empirical correlation in this place. I'm not sure if a tool like Spiral would have that, but it's definitely not something that you could do in your typical simulation tools. I would suspect that's something that you'd have to rely on laboratory or some form of empirical correlation. That's at least what I understand. Yeah.
Okay. The next question comes from Mr. David. And the question is, I would like to have simulation of lactic acid polycondensation into PLA. However, I can't find PLA, which I assume is polylactic acid, on Aspen Plus version 10. I've tried to input monomer data, but when I run the simulation, an error always occurs. Do you know any other way to have simulation of polymers like lactic acid?
Okay, so I need to tell you something. I'm not really a polymer expert. I took one class in polymers in university, so I just know enough to be dangerous. Unfortunately, it's not my area of expertise. What I would recommend highly in this case would be to shoot a question over to Aspen tech support for this, because I really wouldn't know where to start or why that error occurs. I can't find PLA. I've tried to input monomer data. Lactic acid. I would be surprised if they did not have PLA in there. I unfortunately wouldn't be able to. Wouldn't be able to advise for that. But what you do is if you leave your email address in the chat box or something like that, I can ask some of my buddies who are doing polymers and pick some of their brains for that, David. Yeah. So sorry, that's not something that at this point in time I know at the tip of my tongue. But we'll get back to you on that.
Does that mean that David gets a cup?
Yeah, I couldn't answer that. So David, you get the cup, man. So tell us where you're from. You get an East 101. You get an East 101 mug.
Please send us send us an email, and we'll get in touch with you for your question and also your prize. All right, David, thank you. And one more question from Mr. Chiwei. Just out of curiosity, based on the example you mentioned in your talk just now, hitting reset and running the column sim again converges the column. I have encountered this issue several times in my school work. Why and how does that happen actually?
So cannot converge, then you reset and run, reset and run, and it converges. Then you're very lucky. Well, okay. So if you take a look at your distillation column, if you take a look at the way the distillation column solver works, it's a fairly complex solver. And I think by default, if you're using like HISYS, it uses this method called the inside out, the HISIM inside out method for that, where it's actually solving a bunch of nonlinear equations simultaneously. So it's essentially an equation oriented solver. Now, whenever you're solving nonlinear equations, yeah, you you always be using something similar or based on like a Newton-Raphson method. Okay, so if you can remember back from school days, these sorts of nonlinear, iterative Newton-Raphson like or successive substitution kind of methods, you always need to have like an initial guess. Yeah, if you start off with a bad initial guess, sometimes you cannot arrive at your solution. And this all depends on the shape of your function. So if you have like a nice smooth function for a particular area that you're looking at, then it's likely that your solver would take you to your final solution. Why? Because if the example I was using, like Newton-Raphson method, it looks at slope. So it calculates your slope. So if your slope is nice and smooth, yeah, then you can find your solution. If your slope, if it's flat, there's no slope, then no matter what it changes, yeah, whatever change you make, the function doesn't change, you don't find your solution there. If your slope is very steep, you make a small change and then you get to another point, then that's one of the reasons why you can't converge. So one of the things that happens when you press reset is you actually start, you essentially initialize the starting point. Okay, so if you have a function which is maybe somewhere it's nice and then later it's not nice, maybe you might have started at the place where you are having a flattening or like a very steep curve, and you can't, it can't recover, it can't get you the correct solution. It can't go nicely to your solution. But maybe when you reset, it goes back to a state where you are at a point of the function where it's nice and smooth. Yeah. So that is typically why sometimes if you're lucky, you hit reset and run and it's okay. And this typically will happen when you do have the following. When you maybe you've already got a converge case, and then you make a change and you run it again and it cannot converge. This action of hitting reset and restart, generally it doesn't happen when you first build your column. Let's say you build your column the first time, put everything in, and then you run, cannot converge. You reset, run again, it probably still won't run again. It still won't converge. But if you have built your column and then you make a change, let's say you build a column, you did a run and it converged, and then you make a change, and then you hit run again and it cannot converge. In that case, sometimes hitting reset might give you a better starting point. So it generally has to do with starting points. Yeah, reset sometimes gets you back to a better starting point. But again, you still need to have, before you actually start working with the column, have a good initial material balance first. Yeah.
Okay.
Okay.
One more question from Yi, Yi. The question is, some plants like to specify simulation software to be used in their ITB. Is it really that important for them?
You have to ask them, lah. So okay, so it's like this, lah. Let's say if you're a company like Shell. So Shell, the in-house software is Unisim. Yeah. So if you do work for them, then they're going to ask you to do in Unisim. Why? Because then they want to check your work, or they want to use your models. Maybe the part of the deliverable might be the models, because they want to utilize the models for something else. That's why they would specify that in the ITB. So that's generally the reason, like, they want to reuse the models. That is one. Another thing is some companies, you know, when they choose they don't just ask you for a particular software, they will also ask you for the version. Yeah. So if they ask you for HYSYS, they might ask you for HYSYS version 7.3 or HYSYS 10.1 or version 11 or something like that. Why is that? Well, some companies, I think Shell does this. I can't remember if other companies do it, but they would do a checking, a QA, to make sure that the software can calculate the calculations generated by the software meet their standards. So they would have some base test cases. Yeah, calculate duty, calculate surface area, heat exchanger, calculate column, and they might run these test cases which they have validated for the particular software version. And when that software version, if it can calculate within the particular tolerance range, then they would accept it. So that's another reason why, because they have the trust that that particular software can deliver the computations that they want. I think someone got kicked out and wants to come back in. Okay. Yeah, so that's why some people specify the simulation software in the ITB.
Okay, thank you, Rafil. We don't have any more questions for the time being. It's been about 40 minutes since the end of the webinar. I think we'll give it another 10 minutes. Anybody, if you're in the middle of typing a question, please go ahead and type it up in the chat and we'll answer it as best we can.
Okay, I think there's probably no more questions. I think we'll probably call it a day. Let's give it like 30 more seconds. So don't forget to come back on the 3rd of June. Dr. Anwar will be talking about artificial intelligence and machine learning. So that's a pretty hot topic these days. And he's been doing quite a bit of work in this particular area using Python and all the various tools. So it's pretty neat. There's a lot of nice tools out there that can allow you to do these types of analyses. Yeah. So I think we don't have anyone else here. So before leaving, I would like to thank everyone for coming on board for this seminar. We got quite a lot of people joining us. Thank you for that. I had a lot of fun. This is the first webinar I've ever done in my life. So I think there was quite a few things that I learned from this. Now, one of the things I like to do also is for those of you celebrating Hari Raya, Selamat Hari Raya, Aidil Fitri, Maaf Zahir Batin. Hope you all have managed to have a good Raya. This year, I think cannot do no visiting or anything. Maybe you guys can do like a Zoom visiting, but cannot makan. So I just like to thank everyone again. Stay safe, stay healthy, and take care.